Hello guys, I'm back with another video. In this video, we are going to see the patterns of data replication in distributed systems. We are going to be looking at how raft works, how paxes work, how generation clock and replicated logs work. And for this video, I particularly referenced a book called Patterns of Distributed Systems by Unmesh Joshi with Martin Fowler. This is a wonderful book for anyone who wants to understand distributed systems deeply. And also, the PPT of this video is available on the Patreon link. This is the Patreon link for the PPT, guys. I will drop a link below. Please feel free to download it. And yes, this is the pattern of replication in distributed systems. And we are going to be looking at 15 different concepts of data replication used in distributed systems. Firstly, we are having write-ahead log. So write-ahead log means it persists every state change as a command to the disk. For example, if a client requests a transaction and it reaches a particular database, and without committing that transaction, the data is partially written onto the server. And before the data is fully written onto the server went down. So what happens? The partially written data will cause a series of errors. For mitigating that issue, we are using the write-ahead log. What it essentially does is, it writes the transaction and the number and the key and value itself into a particular log file, and this log file will be stored onto the disk. And after once the particular command is stored onto the disk, then the transaction will be executed and committed. So that is the use of write-ahead log, or also known as WAL. And the second thing is segmented log. If we keep on writing the logs onto a single file onto a disk, the file will become larger and it will take more space on the operating system, and the deletion of that particular file will be expensive. For this issue, we are using a system concept called segmented log, which is we are dividing the particular single log file into a series of pixel-sized logs which will be containing the commands. So instead of single file, we'll be splitting the file into a series of pixel log size. And the third one is low water mark. This is the index on the write-ahead log, showing which of the log portion can be safely discarded. So this is the log file above which all the transactions are committed and it's safe to be discarded. And below that watermark is the things that needs to be done. So everything above this point can be cleaned up. There are two types which are widely used. First is snapshot based, which is used by Zookeeper, where each of the snapshots and the log index will be stored on the log file, and after a series of time the snapshots can be safely discarded. In Kafka, these append log files will be stored on a series of time-based frames. It will be stored in the disk for up to 7 weeks and then it will be discarded. And the fourth concept is the leader and the followers. Leader is the single source of truth, and it is the one server that coordinates all the replication across the cluster. And the follower are nodes that replicates the leader's state. And there is one important concept called leader election. There are two types which are mainly used. First is ZAB, which is used by Zookeeper, and Raft. In ZAB, we will be having the leader election. So before starting the leader election, all these followers will be getting started looking up for the leader. If there is no leader, then there will be a leader election. And how the leader is selected is based on the Zookeeper's transaction ID, which is this updation number with the server having the highest transaction ID will become the leader. If there is a tie between the Zookeeper's transaction ID, the server with the highest server ID will become the leader. And after the leader is selected, the generation number will get increased. The generation number is just the phase of the leader election. So this is the implementation of ZAB, and in Raft we will be having all the nodes which is started as followers, and then if it finds that there is no leader, then the leader election, then they will increment the generation number, and then the leader election will happen. In ZAB, after the leader election, the leader got elected, the generation number will get incremented. But in RAF, the generation number get incremented, and then the leader election will happen. The leader will be selected on RAF based on the timeout. So that's the thing about leader election. And then we'll be having leader election using consistent core. Why we use consistent core means if we implement the leader election and voting process and everything across thousands of servers all across the globe, it will become a tedious process. So we will be having a consistent core, or a small group of nodes that maintain a single agreed upon state. These servers and the core will be responsible for the voting process, the leader election process, and everything. After the voting or the leader election is done, that particular state will be extended up to the data plane servers, which could be API servers, schedulers, and everything, and then it will reach the eventual consistency. That's the use of consistent core. And then the fifth concept is heartbeats. These are messages sent at regular intervals to indicate that a node is alive. In small scale, let's take an example of a leader and a server. And if the leader is alive, it will be particularly sending the heartbeats to all the server, indicating that I am alive and I am your leader. Extending this to a large scale means we have to send that particular heartbeat message to the thousands of servers. But it is not possible if the particular leader is get paused for a series of time. For example, there's a pause for the garbage collection, then the other followers will notice that there is no leader and let's start a new leader election. This will result in split brains. So that's why we are having a concept called gossip-based protocol, which is there is no central coordination. Information spreads probabilistically. For example, if one server knows that this is the leader that we are currently following, it will send that state information as a gossip to the next server. For example, if it is on a connection with an n number of servers, it will exchange the state information with that n number of servers. It will happen in a series of push and pull mechanism. If the another server has a more updated state information, it will share it with all the other servers. And in this way, all the state information will be spread across all the different servers on the network. And then the sixth concept is the majority quorum. This is an operation which is mainly based on the acknowledgement of all the servers on a majority. For example, if a particular operation called write needs to be done, it should be acknowledged by more than half the number of the servers on the cluster. Then only that particular proposal will get accepted. For example, here we are having a server which is sending a proposal called write, and it will be replicated across all the follower nodes. And if it is received, the follower nodes will send an acknowledgement stating that, hey, I received a proposal and we are good to go. And then if the majority sends the particular acknowledgement, the server says, okay, let's go ahead and do this particular operation. This is the formula for the quorum. And the seventh concept is the generation clock. Generation clock is just a generation number which indicates the phase of the leader election. For example, here we are having an old leader which is passed due to the garbage collection, and the election will get started and then a new leader will be elected. This can be also known as term, epoch, or generation. For example, here we are having an old leader which is sending a write proposal on the generation 1, and we are already created a new leader because of the garbage collection time pause with the generation 2. If the both of the leaders are sending a particular proposal to the follower systems, the systems will be only accept the proposal from the server with the highest generation. Log with the highest generation will get replicated. And the eighth concept is commit index or high watermark. This is an index on the wall showing the latest successful replication. For example, we got a log file. For example, this is the problem that the commit index solves, guys. So we are having a log file and there are two operations, write and read commands. Firstly, the leader is sending the write command to all the followers, and the followers are processing that request, and suddenly the leader gets down, and this log file is discarded on the server side, and the next command for the follower servers to execute won't be there. So how will the followers know? For that, we are having a particular, we are having the commit index. So firstly, wall will have all the log files that are included in this, and then it will append it to the leader, and then the leader will send a replication request stating that, hey, use this, this is my log file, please update your log file with this particular one. And all the follower servers will compare the request and then update it. And then if they update it, they will get to know the next command they need to execute. If there is also a concept called log truncation, which means the entries with the same log index by lower generation clock or loop. Let's just say that the first 3 entries are done on the generation 3 and they are committed, and the commit index is below the 3rd entry, and then the 4th entry starts. Here, the leader will then remove and discard all the lower generation entries and start fresh with the new log file. And this log file will then be replicated across all the servers, all the follower servers. And moving on, we are having the 9th concept, Paxos. So Paxos is a 2 consensus building phase algorithm, which is used for reaching safe consensus even if the nodes disconnect. There are 3 main nodes involved in Paxos. They are proposer, acceptor, and learner. Proposer suggests a value, and the acceptor, if there was a promise, it will vote on the proposal, and the learner will learn from the chosen value. There are 2 phases in Paxos. Firstly, we are having prepare phase, and second, we are having the accept phase. So the first phase, prepare. Here, let's just say that a server with the proposal number 1. Proposal number is a series of incrementing positive number for each of the proposals. It sends that, hey, I have a proposal, so please accept it. Accept this number. So the proposal will send a prepare request to each of the follower nodes. So the followers, which are acceptors, responds with a promise, say that, hey, we are accepting your proposal. So this proposal promise will only get accepted if the proposal number is greater than the last accepted proposal number. And then if the prepare phase is done, then the acceptor phase will come into picture. In the acceptor phase, the proposer will send the value. Hey, for the first proposal number, this is the value that you need. This is the value or transaction or query that you need to perform. And then this accepted value will then be sent to the acceptors. This proposed value will then be sent to the acceptors, and the acceptors will respond with a promise like, hey, we are accepting your proposed value and we are good to go. And if the acceptor receives an older proposal with a value, if the value is less than the current accepted value, it will discard the older value and go ahead with the new value. And the 10th concept is the replication log. This is mainly used for keeping the state synchronized across multiple nodes on a cluster. It's just the same as that we have seen in the commit index. It's just the wall is appended, the wall log gets appended into the leader, and the leader will send a replication request, and replication request logs will be replicated onto each of the follower nodes. And the 11th concept is the singular update queue. In the singular update queue, we'll be using a single thread to process the request asynchronously to maintain order without blocking the caller. Let's say that we are having 3 threads with a particular process called heartbeat timeout, node registration, and admin command. And then these threads will be enqueued into a queue. And from that queue, we will send the process to a single thread, and this thread will process that particular function or heartbeat timeout and everything, and then it will complete that function. So why we are using a single thread for processing the request? Because we will be having exactly 1 consumer and 1 active mutation, which is the change. And this also removes the logs and complex concurrency control and hidden race conditions. And there is the concept called back pressure, which is if more number of processes gets enqueued onto the queue, the capacity of the queue becomes full. So the other processes that are coming will get blocked, rejected, retried, or slowed down. For mitigating this, we are using a concept called reactive streams. This is the most and widely used concept, which is allowing the customers to control the rate at which the producer emits the data. Which means if the consumer didn't ask, hey, I need 3 of your data, the producer will not emit the data to the consumer, that way to the processing queue. So it works on subscriber, publisher, and subscription process. So firstly, the subscriber is the consumer. It sends that, hey, I want to subscribe to your particular data. And the publisher will send, okay, which means, okay, we can produce the subscription. And then the subscriber will send a request stating that, hey, I need n number of data from your data source, from the publisher. And the publisher will send that 3 data to the subscriber, and then it will say that, hey, I sent all your data. It's the completion. That's the entire thing about reactive stream. If you don't ask for it, it won't send to you. So this is also used in Spring Webflex for concurrently controlling all the requests. And moving on, the 12th concept is the request waiting list. This is used for tracking the client request, which request response after a particular criteria is met. For example, let's just say that a process is coming in, and the particular command that is executed by the process requires some backend works. For completing that backend works and everything, this particular process will be put inside a data structure known as purgatory. So this purgatory will contain all the processes that needs extra processing or needs to perform extra process. If the incoming requests don't have any other process to complete, it will just go ahead and complete. The structure of the purgatory will be based on watch list, which is the index of the request, the request number, and everything. And it also has timeouts, which means a process can only rest inside the purgatory for a series of time. And callback means if the process extended function is completed, which means the required function is completed, then the process will be moved out from the purgatory for the next level, which is the completion. And the 13th concept is the idempotent receiver, which means we have to identify each request uniquely, which helps us to ignore the duplicate request when the client retries. For this, we are using client identifier and request number. So firstly, let's just say that a client is sending a request, and this contains the client identification number and the request number. And once this request reaches the consistent core, which are the series of servers that we are having, the client will register itself with the server with its unique client identifier number. So this in turn creates a client session which will store the request number and the series of response that is sending for the particular request. There are almost 3 types. So for example, if the client is retrying that same request again, then it will check for that request number in the session, and if the request number is already processed, it will just send the response to the client again, at most once, which means the client is not retrying again. So the request process will be done only once, and at least once means the client is retrying again and again, and the request is processed again and again. Exactly once is the idempotent receiver, which means we have to process the request exactly once, and the response will be stored on the session and it can be reused again. And then the 14th concept is the version value, which is we are storing every update with a new version value. This is the main concept used in multiple version concurrency control, which is obviously used in Postgres. This uses 2 things. Firstly, a reader will always read an old and fixed snapshot. For example, let's just say that a client wants to read a particular balance. We are having these number of balance version 1 and version 2, and the snapshot is set to version 2. then the client will only read what is on the snapshot of the version 2, which is 150. And that is about the read. And when the write occurs, the write never overwrites. It only adds a new version. For example, we're having the version 3 as 200. It will only write it as a new version, not overwrite the already existing value. And then the snapshot is again sent as V2, not as V3. Then you may ask, so the updation happens, won't be the client getting the new updated result? No, eventually, of course, after the reading finishes, nobody needs the snapshot less than or equal to version 2. So the system deletes everything up to the version 2 in the garbage collection app, of course, after a sequence of timeouts. Then it will update the snapshot to the version 3. Before the deletion also, the snapshot can be set to version 3, and the deletion can be after the updation of the snapshot. The main thing of MVCC is consistency is more important than freshness. And the last concept, version vectors. These are set of counters, one for each node, to detect the concurrent updates. In the version vectors, we will be having a series of nodes with the updated version numbers. For example, here A equals 3 means there are 3 times updation happened on node A and B and C. So for example, in node A, before updation, the A is 1, B is 0. After updation, the A becomes true, which means that it gets updated. And if it comes in contact with node B, it can exchange the state information of the version vector. In this node B, we are having the local as A1 and B2. On the remote side, we'll be having A2, B0, which is the version vector of A. And then after merging, we will get a series of merged version vectors. So why version vectors? So these are used to detect conflicts. For example, if there is an updation required on the value of A, both node and node B update at the same time, then the version node for A will become 2, A will update to 2, and then in the version 2, which is on the node B, it will update to 1. It can be resolved by CRDTs, conflict-free resolution data types, using associative commutative and idempotent properties, and last write wins, which is the last write that has been done wins. This is not an efficient way, but Cassandra uses it. So that's it, guys. This is the entire 15 data replication concept used in distributed system, and I think I've covered everything. If you have one more tab, please drop it down on the comments. Let's just learn from everyone. And that's it, guys. Please like, share, and subscribe, and see you guys again with the next awesome video. Bye bye.